I'm always very thankful for the question because it allows us to explain a bit about our philosophy. And the question is like, why do you so in the speaker this much? Einwinkeln in German. I learned the verb. There's a good reason for it. It's part of our strategy to actually make the speaker room combination more predictable and to have the less impact from the room on the total result. And there will never be a world where the room has no influence on the acoustics, but a speaker design in a certain way can help. And there's two fundamental room problems. One is the room modes, that's at the lower frequency of the spectrum, and the other one is reflections to walls or maybe ceilings, or those reflections offer travel a longer way compared to the direct sound. So they arrive later at the ear, and when they arrive later, they muddle the sound. They interfere with the sound, with the direct sound, in a way that's very nasty. So we want to reduce the energy that's actually in the reflections itself. That's our strategy, actually, to attack the room. And there's a few ways of doing so, and one way is to make a speaker more directive. So it has a less energy to the sides. At the low end, nearly every speaker is an omnidirectional system, and the higher the frequencies, the more directive it becomes. So if you're behind the speaker, you will have more low frequencies than before the speaker in front of it. By making the baffle wider, the speaker will become more directive for the lower frequencies. That's one of the strategy parts. And the other one is if you turn it in, if you tow it in, you have even less energy radiated towards the walls. So it's a strategy. And you could argue with me like, okay, but then I'm not listening on axis, I'm listening actually off axis. Because on axis is there and you're like there. And that's a good point, and we took that into our development and calibration of the speaker, and actually the speaker is linear off axis, 15 degrees off axis. So physically you may be off axis, but acoustically you're on axis. And there's a second advantage to doing so. If you're outside the center of the two speakers, you are more close to, for instance, to that speaker, and that's why it's louder. But you're more off axis to that speaker, and that's why it's less loud. And the opposite holds for the other speaker. You're more on axis to that one, it's louder. But you're wider away, further away from that speaker, so it's less loud. And this gives a kind of balancing in the sound pressure level across the left-right position of your listening space, and that gives a more relaxed and flexible way of experiencing music. So there's a few acoustical tricks we applied, and we didn't invent them ourselves, just to be clear. It's all old knowledge. This the wide baffle stuff is from Olsen from 1955, but we just apply it in a very straight way, and then we get a certain character of the speaker, which is making it more easy to place in a room. I'm not saying it's like that, you put it in place. It is still critical in terms of interaction with the room, but it's less critical than other designs. So while I'm at it, and then I'll play music, there's another very apparent design issue. That's the rounded corner. That's on purpose. The rounded corner avoids diffraction at the normally very hard side of a cabinet. When air travels or a wave travels across the baffle, it looks around the corner and it sees actually a much bigger volume of air. And just at that very edge, the acoustical impedance changes instantly. The wave scares off of that and travels back. And when it travels back, it again interferes with the original wave, and that gives a very nasty coloration of the sound. So what we did is we do not have a sharp edge where it instantly changes, but we round it off where the acoustical impedance gradually changes and the wave is not scared off that hard compared to the sharp edge. So it's to reduce the edge diffraction. And while I'm at this subject, I'm looking at you, Bjorn. I'm a bit scary to explain this because we have an expert on this in the room. It's an expert on horns, and you do the same. You are dealing with acoustical impedance transitions in horn design, and that's all. I shouldn't say it's not new, but it's sometimes forgotten. It's sometimes forgotten because for other reasons cabinets are made in a different shape. For good reasons, I'm fine with that, but we're here for the best sound that we can get in a certain environment. So that's a bit of the background of the acoustic design. So this is a typical form follows function design loudspeaker. You could argue with me, and then I won't play music, like, hey, you just talked about edge diffraction, but there's an edge here. Well, we looked at rounding off the top. It looks very ugly. So we had to leave that. And that's the reason why the tweeter is at the lower end of the cabinet. The tweeter is farther away from that edge. That means that the diffraction arrives later back to the tweeter, that late that it's less of a problem. But the other edge is nicely rounded. So that's a bit about the acoustical design. A very short introduction in the system that you're listening to. I'm currently streaming music through our MU1 streamer. That's a Roon server, Roon endpoint, digital processing, volume control, digital output to the LS1 speakers. The LS1 system is a fully active system, but it also has analog inputs, and the analog inputs are driven by our new PW1 phono stage, driven by a Dr. Feikert turntable. I will play some vinyl later on. But first, some other music.